Let us now look at the second example where we are going to consider a simple mixing process. Unlike example 1, this example shows the presence of two inlet streams, as you can see. The other aspect of this example is that there are concentrations, different concentrations that we are going to work with, right? So that is the other variation or build up over example 1. We are not going to have any reaction or heat effects here again. That's the similarity between example 1 and example 2. So it's a simple mixing process. There are two inlet streams and one outlet stream. No temperature effects, so I can assume that all the streams have the same density. And we assume the density is the same and they are constant over the entire duration of operation, etc. And we are going to operate the system at constant volume, right? The constant volume V is assumed here. This assumption need not be there. We can always have, variable volume, and we can always write an equation for the volume as dV by dt is equal to Q1 plus Q2 minus Q, right? So this is the equation we can write based on what we have learned in example 1. So we can assume that volume changes with time, and this would be the equation then if we do not make this assumption. But once you have made this assumption that the volume is constant, that simplifies things, because if the volume is constant, dV by dt is equal to 0, which means Q1 plus Q2 is going to be equal to Q. So this Q is going to be exactly the addition of Q1 and Q2. So the inflow amount, total inflow amount, is going to equal the total outflow amount. So that is what the statement says, and therefore V would be constant. All right, so these are the assumptions that we write. This is a schematic. So what is shown here is a stirrer, and this stirrer, what it does is it homogenizes the contents of this tank. That means at any point within the system, right, within this liquid volume here, the concentration would be C. It will be uniform, right? And the value would be denoted by the symbol C here. So I'm not saying C is going to be a constant. In fact, C can change with changes in Q1, C1, Q2, C2, etc. So C1, C2, Q1, Q2 determine the value of the concentration C. So if any of these four variables change with time, C will change with time. So C is not constant necessarily, but C is uniform, right? Throughout the vessel, throughout this liquid volume, C is uniform. So there are no places within this reactor where concentration is different from any other location within this reaction volume or within this vessel volume. So C is uniform, and that is the job of the stirrer, right? So the stirrer is assumed to be ideal. That means there are no dead zones and stuff like that. That means the material doesn't go here and accumulate in these corners and just stay there, etc. It's completely well mixed. So it is called a well mixed reactor, or it is called a mixed flow reactor, MFR, or it is called continuous stirred tank reactor, CSTR. Of course, here there is no reaction. It is just a well mixed vessel, right? Or a continuous stirred tank vessel. Okay, so that is the basic things about assumptions, about the system, a schematic of which is drawn there, and so on. Now, the other thing that we need to do is we need to prepare a table of this. In fact, if you look at many journal articles, or if you even look at textbooks that talk about such systems, they would always have a section where they will have nomenclature. So they will specify what each symbol means in their mathematical model, what is the physical description of that system, what are the measurement units for that variable, etc. Right? So it is always good to have a kind of a list of variables, what their physical meaning is, and what are their units. Right? So it is on in that sense I'm doing this here. So Q1 and Q2 are the volumetric flow rates of stream 1 and stream 2 respectively. So Q1 is the volumetric flow rate of stream 1, Q2 is the volumetric flow rate of stream 2. The units of each of them is in meter cube per minute because it's a volumetric flow rate. Now, the symbol Q stands for volumetric flow rate of the stream leaving the tank, and the unit is also meter cube per minute. C1 and C2 are compositions. Here we talk about salt, right? So it's basically a stream that contains salt. Both the streams contain salt. The salt composition in stream 1, C1, has got the units of kilograms of salt per meter cube. Okay, so that's the units that we are going to work with, kilograms of salt per meter cube for both C1 and C2. And the salt composition of the exit stream is also in the units of kgs of salt per meter cube. The symbol is C. So interestingly, right, because of this well mixed assumption, at the vessel exit, the concentration will be the same as what is inside the vessel. So the moment any volume, liquid volume, falls from this stream or from this stream, it falls into the vessel here, into the mixer here, the concentration will reach a value C. It will be homogenized. And because this fluid stream that comes out from the vessel is drawn from the vessel, the stream will also have the same concentration as the interior of the vessel, right? As what is in the interior of the vessel. So I hope that is clear now. And V is the volume of the liquid in the tank, right? What is the volume of tank contents, and the units would be meter cube. So here, let's see how to proceed. Again, we observe the system between time t and t plus delta t. So we start looking at the system at time t and stop looking at the system at t plus delta t. So we are looking at the system for delta t, duration of time. And we are assumed that volume is constant. Therefore, as we wrote in the previous slide, Q is equal to Q1 plus Q2. So this is something that we can write straight away because of assumptions of constant density again. Mass is conserved, as we know, and since density is constant, what we can write as mass rate in is equal to mass rate out kind of an equation. And if you divide that by density, you will get volumetric flow rate in is equal to volumetric flow rate out at steady state. That means when V is constant. So we have that. Now let's focus on the salt, right? So if you look at the salt balance, so the equation is very clear. What is the mass of salt in the tank at time t plus delta t minus the mass of salt in tank at time t? So if you take the difference will tell us the mass of salt that got accumulated in the system during this time interval delta t. So within this time interval delta t, how much salt has accumulated in the system? This difference will give us that quantity. Now, on the boundaries, what has happened is there are streams that bring in salt and there are streams that remove salt. So what is the mass of salt that enters the tank via the inlet streams during the time interval delta t minus what is the mass of the salt leaving the tank during this time interval delta t via the exit stream? So this is like income of salt, right? It comes from two sources. This is the expenditure of salt that goes out from as one stream, and the difference between the two amounts of salt, that is what is going to be accumulated in the system, because whatever salt comes in either must go out or get accumulated within the system. There is no formation of salt, there is no consumption of salt in the system, there is no reaction. So whatever comes in either has to go out or must accumulate within the vessel. This equation basically states that. So what we do is, what is the mass of salt in tank at time t plus delta t? Consistent with our definition, V is the volume of the tank contents, so that's in meter cube, and the concentration in the vessel is C. The units are given to be kgs of salt per meter cube. So if you multiply the two, meter cube and meter cube will cancel, leaving you with kgs of salt. So that's the mass of salt. So the mass of salt is Vc at t plus delta t, because we are looking at how much is the amount of salt at time t plus delta t. So we say V times C at t plus delta t. Again, the mass of salt in the tank at time t is given in a similar manner, except that we say Vc that is evaluated at time t. So Vc evaluated at time t. That's what the second term is. So that is going to equal what is the mass of salt that enters the tank during this time interval delta T. So through stream 1, Q1 is the volumetric flow rate of stream 1, right? The units are meter cube per minute as we have seen there. So this is in meter cube per minute. Stream 1, input stream 1, the concentration of salt is C1. This is in kgs per meter cube. So if you multiply Q1 and C1, you're going to get kgs of salt per minute. So you have to multiply it with a time unit. So you get Q1 C1 delta T. That is the amount of salt that has come in to the system through stream 1 over this time interval delta T. Again, through stream 2, we are going to get Q2 C2 delta T. This is the mass of salt that comes into the system during the time interval delta T or over the time interval delta T through stream 2. So these are basically, if you take delta T outside, because that's common in both the terms, you can write this. Now, what's the salt that leaves the tank during the time interval delta T? So again, using the same combination of variables, it's going to be the outflow volumetric rate multiplied by the outflow concentration multiplied by the time. So it is going to be QC delta T. This is the amount of salt that leaves the tank during the time interval delta T. Now, as usual, what we will do is we will divide throughout by delta T. So when we do that, when we divide by delta T, we get V times C at T plus delta T minus V times C at time T divided by delta T is going to be Q1 C1 plus Q2 C2 minus Q times C. And what we can do is in the limit that delta T approaches 0, right? In the limit that delta T approaches 0, the left-hand side will reduce to d by dt of V times C using the basic definition in calculus, right? So we can do that, and the right hand side will still be Q1 C1 plus Q2 C2 minus Q times C. And since V is constant, we can take V out of this derivative. So it is going to become V dC by dt is equal to Q1 C1 plus Q2 C2 minus QC. And then once you recognize that Q is going to be equal to Q1 plus Q2, so we can write the right hand side as Q1 C1 plus Q2 C2 minus, instead of Q, we can write Q1 plus Q2 times C. And that leads to this equation that you see inside this box. So this is the mathematical model for this simple mixing process that takes place in the tank.